Welcome back to the deep dive. You've shared your sources, and today, well, we're executing what I think is the ultimate shortcut to expertise on a really critical foundational concept in cloud architecture.
Snowflake table structures.
Exactly. Snowflake table structures.
Yeah, tables are, they're the absolute bedrock, aren't they? They're these database objects structured, logically rows and columns,
Right.
where all your data in Snowflake ends up living. Structured, semi-structured, even unstructured now.
But just thinking of them as one single thing, a table, that's really a mistake, isn't it?
Oh, absolutely. A big one.
And that's the whole point of this deep dive today. Our mission really is to get past that idea of just a standard table. We want to dissect these specific, tailored table types. We're talking permanent, transient, and temporary.
Yeah, and understand why. Why an architect, why a data engineer chooses one instead of the others.
It's all about using the right tool for the job, isn't it? These are specialized tools designed for, well, managing the data lifecycle.
Optimizing it,
Maximizing recovery options, and maybe most importantly for a lot of folks, radically controlling your cloud costs, your expenditure.
And you really can't talk about recovery and cost efficiency in Snowflake without starting with those two core features, the ones that really differentiate these table types.
Time travel and fail-safe.
Exactly. Time travel, that's your immediate safety net, right? Your self-service recovery window for, let's be honest, user errors.
We've all been there.
And then fail-safe, that's different. That's the platform's own kind of lockdown extreme disaster recovery protocol.
Understanding how those two concepts, which are really distinct, how they intersect with how long a table sticks around, its persistence.
That's the key. That's probably the single most important thing you can take away from our chat today.
Okay, let's do it. Let's unpack this core trio. We should probably start with the baseline, right?
Yeah.
The one everything else gets measured against, permanent tables, the default standard. So permanent tables, these are kind of the default workhorses. Yeah, they are. They're exactly what you get if you just run a standard create table command. No special keywords needed.
You don't have to explicitly say permanent or anything?
Nope. Because they represent that standard expectation, durable, long-term data storage. That's what most people think of when they just say table.
Right. Makes sense.
They're the ones you'd use for your really important stuff. Your fact tables, your dimensions, any data asset that's truly core to the business. For operations, for reporting.
So using them means you're basically making a full commitment. You're saying this data needs to persist and I need the maximum recovery assurance possible.
That's it, exactly. Full commitment.
And commitment, especially in the cloud, well, it always comes with a price tag attached. So what are the cost implications of deciding something needs that level of permanence?
Well, the permanence hits you in two ways, really. First, obviously, the data itself takes up space.
Sure. Standard storage costs.
Standard storage charges, yeah. For as long as that table exists. But second, and this is often more significant when you think about the long-term cost of your architecture, permanent tables come with that full insurance policy. They include the highest level of recovery features Snowflake offers. That means both time travel, the user-driven one, and fail-safe, that internal, non-user accessible protection.
Okay, so when an organization looks at a data set, maybe it's, financial transaction history,
Perfect example.
and they decide it's critical, they're essentially signing up to pay that premium, the cost associated with keeping the data blocks around for both time travel and fail-safe.
Precisely. You're paying for the best case scenario, for data availability, for recovery options, because, well, you're betting your business on that data.
Yeah, if your most critical data just vanishes.
You need that guarantee. You need to know Snowflake can help bring it back, whether it was just a small user mistake, someone dropped the wrong rows.
Covered by time travel.
Covered by time travel. Or if it was some massive unforeseen catastrophe impacting the platform itself.
Covered by fail-safe.
Covered by fail-safe. So the syntax, like we said, it's the default. Super simple.
Oh.
Just create table employee, chat number, name varchar, no frills needed.
Okay, that's permanent. Now let's shift gears to transient tables. This feels like where the conversation really pivots towards strategic cost management.
Yes, it does.
I kind of see transient tables as maybe the ultimate compromise for data that's important, but maybe not that important, or maybe for intermediate data.
That's a good way to think about it. Transient tables, day to day, they function almost identically to permanent ones.
Okay.
They stick around across sessions. Other users can see them. They only disappear when you explicitly drop them.
So they feel permanent in use.
They do. But the difference, the core difference, is entirely rooted in how you classify that data and your philosophy on recovery for it.
So if permanent tables are for your, let's call it P1, mission-critical data, where does Transient fit in that priority scheme?
We typically see Transient used for P2, maybe P3 data. Stuff that's non-critical or, and this is a really common use case, data that you can easily recover or recreate from somewhere else if you absolutely had to.
Like from an external source.
Exactly. Think about staging layers, right? Where the raw files are still in S3 or Azure Blob, or maybe intermediate results from a big transformation pipeline, or even massive log ingestion tables where the original logs are kept cheaply somewhere else.
Gotcha. So this is where that recovery trade-off becomes really, really strategic. What exactly are you giving up? What's missing from that insurance policy when you declare a table transient?
The key difference, the big one, is the intentional removal of the failsafe feature.
Ah.
Transient tables simply do not have a failsafe period, full stop. They also only have a very limited time travel period. Usually it's capped at just 1 day or even 0.
0 or 1 day for time travel and 0 days for failsafe.
Correct. So by choosing Transient, you're making an explicit decision. You're saying paying for that long-term extreme disaster recovery guarantee provided by failsafe, it's just not necessary for this data.
And getting rid of failsafe, that's where the big cost savings come from, right? Can you unpack that a bit? Why does avoiding failsafe costs matter so much to, well, the bottom line?
Oh, it's a huge architectural lever for cost. Remember, failsafe isn't just a flag. It represents an extra 7 days of actual stored data retention after your time travel window expires. Now imagine you have a multi-petabyte environment.
Okay.
Maintaining those 7 extra days of data blocks, plus all the operational overhead for Snowflake to keep that data accessible internally just in case. That represents a substantial recurring expense on your storage bill.
So by using transient tables and just skipping failsafe entirely,
you eliminate those storage costs, the costs associated specifically with maintaining that deep internal disaster recovery layer. Gone.
So it becomes a strategic calculation. If losing, say, 7 days of an intermediate staging table just means I have to rerun an ETL pipeline for a few hours, that's potentially far, far cheaper than paying the storage cost for that 7-day fail-safe window on potentially terabytes or petabytes of data for an entire year.
Absolutely spot on. Think of it like this. Permanent tables are like putting your absolutely critical business documents in a super secure, temperature-controlled vault with triple redundancy built in.
Yeah.
That's fail-safe.
Maximum security.
Transient tables are more like putting, say, non-critical documents, things you could easily reprint or reconstruct, in a standard filing cabinet in the office.
Okay.
They stick around until you decide to throw them out, right? They persist. But you haven't paid that premium vault security fee because, well, you can get them back another way if needed.
And making that choice, that has to happen right at the beginning when you create the table.
Yes. It requires using the specific keyword, create transient table employee, ID number, name varchar. You have to declare your intention up front. Temporary tables, the session scoped utility.
All right, that brings us to the third type. Temporary tables. These feel fundamentally different again. They aren't really about persistence in the same way, are they? More like a short-term utility.
Correct. Completely different purpose. These are purely transitory data stores. Their entire definition is based on their scope.
Scope meaning?
They exist only within the specific session in which they were created. That's it. Think of them as your own personal, private workspace for that session.
So if I'm in a Snowflake worksheet and I create a temporary table, nobody else in my organization can see it.
Nope.
And even if I open another worksheet, another session myself, I can't see the temporary table from the first session.
Exactly that. Not visible to other users, not visible to other sessions. It makes them perfect for things like complex multi-step calculations where you need to store intermediate results.
Or maybe testing out a big transformation on a sample of data.
Yeah, or dealing with sensitive data that you need to materialize just for a moment, but you absolutely do not want lingering around in persistent storage afterwards.
And their defining feature really is that absolute destruction policy.
It is. It's guaranteed. Once that session ends, maybe you log out, maybe the connection just times out, maybe you close the worksheet window.
Doesn't matter how.
Doesn't matter how. The table and all the data in it is completely dropped. And crucially, it is not recoverable. There's no safety net built in.
It's like writing notes on a whiteboard, right? You wipe it clean when you leave the room and those notes are just gone.
Perfect analogy. Gone.
Okay, so in terms of those recovery features we talked about, time travel and fail-safe, where do temporary tables sit?
Functionally, they're identical to transient tables in that regard. They lack a failsafe period entirely.
Zero failsafe.
Zero failsafe. And they have that same very limited time travel period, typically just 1 day or sometimes 0, depending on configuration.
But here's something interesting I saw in the sources, an operational insight. Even though Snowflake guarantees will be dropped automatically when the session closes, the recommendation is still to explicitly de-drop large temporary tables yourself when you're done with them. Why bother with the extra step if cleanup is automatic?
Yeah, that recommendation comes down to, well, avoiding unexpected costs and just good operational hygiene.
How so?
Well, while temporary tables will eventually get cleaned up by Snowflake, if you generate a massive amount of intermediate data in a temporary table,
Right.
that data still temporarily consumes storage space. It still contributes to I/O on your warehouse cluster right up until the moment it's actually purged or the session truly terminates.
So if a session stays open for a really long time, maybe like a long-running data science notebook connection or some specific automation tool that keeps a session alive.
Exactly. In those scenarios, that temporary data could hang around consuming resources for longer than you expect.
Yeah.
Explicitly running a drop table as soon as you're finished with it immediately frees up those resources.
Okay.
It prevents any unexpected temporary spikes in storage usage showing up on your bill and just keeps things tidier. Avoids accumulating data that genuinely serves no purpose anymore.
So good practice is proactive practice, even if cleanup is guaranteed eventually.
Precisely. And again, creating them requires that explicit keyword, create temporary table employee. Added number, name varchar 50.
Okay, we've kind of established that time travel, TT, and failsafe, FS, are really the levers that define this balance between persistence and cost for the different table types. Now, let maybe dig just a bit deeper into the technical mechanisms, because the difference between TT and FS isn't just like a policy setting. It reflects a difference in the underlying storage architecture.
Absolutely. Let's start with time travel. Like we said, TT is the user's lifeline. It's what allows you to access historical data. Data that's been changed, maybe deleted, maybe even the whole table got dropped.
Right.
As long as you're still within that defined retention period for time travel.
Now, the genius here, as I understand it, isn't that Snowflake is making full copies of the entire table every time someone runs a UP-date statement. That would be crazy expensive.
Oh, prohibitively expensive. Yeah.
So how does time travel actually work behind the scenes? How does it enable that fast rollback capability?
Okay, this gets us into Snowflake's core storage architecture. It revolves around immutable micropartitions.
Micropartitions, okay.
So when you update data or you delete data in Snowflake, it doesn't actually go find the existing data blocks on disk and modify them in place. That's not how it works.
Right.
Instead, it writes new micropartitions that contain the change data. The old micropartitions, the ones with the data before the change, they get flagged internally as like pending deletion.
Okay, so they're not immediately wiped out.
Not immediately purged, no. And time travel essentially works by maintaining the metadata pointers. It keeps track of those older pre-change micropartitions for a set period.
So if I accidentally run a UP-date statement that messes up all my data, time travel lets me basically query the table's metadata from, say, 5 minutes ago, before the mistake.
Exactly. And Snowflake's engine uses those older metadata pointers to reconstruct the state of the table using the micropartitions that existed then, the ones that haven't been garbage collected yet.
So it's really a clever metadata management trick.
It is. And that retention period you set for time travel, let's say you set it to 7 days, that's simply the time window during which Snowflake guarantees it will preserve those older micropartitions and keep the metadata pointers available for you to use.
And that applies even if I drop the whole table.
Yep. If you drop a table, the table object itself is marked for deletion, but the underlying data blocks, those micropartitions, they stick around until that time travel period expires.
Which makes time travel absolutely crucial for those common oops moments, right? A bad data load script, accidentally deleting a bunch of rows, dropping the wrong table entirely.
All the classics.
It's instant or near instant self-service recovery, which explains why organizations using the Enterprise Edition often crank that time travel window way up, sometimes even to the maximum of 90 days.
User-driven recovery. That's the key phrase here. You, the user, run the command to query the past or restore the data. And that flexibility, that's part of what you're paying for in your standard storage charges when you use permanent tables during that time travel window.
Okay, user-driven recovery via time travel. Now let's pivot to the other one, the much more opaque feature, failsafe.
Way FS.
If time travel is the user's oops button, failsafe feels more like the platform's break glass in case of emergency button, like the nuclear option.
That's actually a pretty good way to frame it. Failsafe is, first off, mandatory for permanent tables, and it's non-configurable. It's always a 7-day period.
Always 7 days. Okay.
And crucially, this 7-day period starts immediately after your configured time travel retention period ends.
Okay, so they don't overlap. Time travel finishes, then failsafe begins.
Exactly. So if your time travel is set to just 1 day, failsafe runs from day 2 through day 8 after the data was changed or dropped.
And if I've paid for Enterprise Edition and set time travel to the maximum 90 days?
Then failsafe runs from day 91 through day 97.
Right. So let's say my 90-day time travel window closed last week. And now, today, I suddenly realize I desperately need data that was deleted 95 days ago. It's within that 7-day failsafe window.
Yeah.
Can I just run some kind of failsafe recovery command myself?
No. And that is the absolute critical distinction. It's the reason why choosing transient tables to avoid failsafe is such a significant architectural decision.
Okay.
Failsafe is explicitly not provided for user access to historical data. You cannot query it. You cannot initiate a restore from it yourself.
So what is it for then?
It is locked down. It exists exclusively for Snowflake's internal use. It's there to allow Snowflake support to potentially recover data that might have been lost or damaged due to really extreme operational failures within the Snowflake infrastructure itself.
Whoa. So we're talking catastrophic platform issues, like maybe hardware corruption at a massive scale or some kind of system-level problem totally beyond any user's control.
Precisely. Think worst-case scenarios impacting the platform's integrity.
Mm.
It's Snowflake's own internal backup plan, their safety net for maintaining compliance guarantees and data integrity against major internal system threats.
And because it's for those extreme platform-level situations.
Recovery from failsafe is not automatic. It requires direct intervention, investigation, and approval from the Snowflake support team. It's a manual, support-driven process for true disasters.
You know, I found this aspect really fascinating reading the sources. Failsafe data is essentially this hidden storage cost, isn't it?
Mm-hmm.
For permanent tables, you're paying for an extra 7 days of storage. But it's storage you, the customer, can't directly access, can't query, can't manage yourself. You're paying for it just in case the absolute worst happens within Snowflake's systems.
Exactly. And that really highlights the massive cost difference compared to transient. When you commit to a permanent table, you commit to paying for those 7 days of inaccessible disaster recovery level storage resources indefinitely, for as long as that table exists until it's dropped and passes through its own time travel and failsafe windows.
So if you have, say, petabytes of log data that gets regenerated every single day,
paying that 7-day failsafe premium on data that's essentially disposable after a short period, that's likely a gigantic waste of money.
and that's precisely why transient tables exist, to give you a way to save yourself from paying for that premium, non-user accessible internal insurance layer when you've decided you don't need it for that specific data set.
Correct. The comparison matrix, availability, TT, and FS.
Okay, this is great. Let's try and synthesize all that architectural detail. Maybe put it into a simple comparison matrix just to make it crystal clear which table choice buys you which level of resilience and implicitly which cost profile.
Yeah, matrix is perfect. And what's really striking when you lay it out, like this is how clearly it shows that spectrum, cost versus durability.
Mm-hmm.
It really forces you to consciously align the table type with how volatile your data is or how critical it is.
Okay, let's start at the low end of the durability spectrum.
Yeah.
Temporary tables.
Temporary table, availability, only for the remainder of the current session. That's it.
I'm gone after that.
Gone. Time travel. 0 or maybe 1 day, typically 1 day by default.
Okay.
Fail-safe period. 0 days, none.
So basically, disposable data, the volatility is like 100%. Once your session is done, it's effectively gone immediately or very soon after.
Yeah, exactly. Targeted for deletion right away.
Okay, next up the scale, transient tables. These give you persistence across sessions, but they keep that minimal recovery profile.
Correct. Transient table availability. It lasts until you explicitly drop it, just like a permanent table in that sense.
Stays around.
Stays around, but recovery, same as temporary. Time travel is just 0 or 1 day. And crucially, fail-safe is 0 days.
Still no fail-safe.
Still no fail-safe. So this becomes the really strategic choice, especially for architects using Snowflake's Standard Edition, where you don't get extended time travel anyway.
Right.
If your data needs to stick around for days, weeks, maybe months, but you've determined it is recoverable from the source if the absolute worst happens, Transient is your go-to choice to save on paying that fail-safe storage premium.
Makes sense. Okay, now for the top tier. Permanent tables. This is where that full insurance policy kicks in, but it depends a bit on your subscription level, right?
It does. Let's take permanent tables in the standard edition first. Availability. Same as Transient. They last until explicitly dropped.
Okay.
Time travel. Still limited, capped at 0 or 1 day. Just like Transient and Temporary in Standard Edition.
Ah, okay. So TT is the same across all three in Standard.
In Standard Edition, yes. But here's the critical cost-driving difference for Permanent Standard. You get that 7-day fail-safe period included.
The platform recovery guarantee.
Exactly. So even if your user-driven time travel window is minimal, just 1 day, Snowflake still provides that 7-day internal recovery buffer via fail-safe.
Gotcha. And now for folks running on the higher tiers, Enterprise Edition or above, what changes?
Big change in flexibility. For permanent tables and Enterprise and higher editions, availability is still standard, lasts until dropped. Fail-safe is still that mandatory non-negotiable 7 days.
Still 7 days FS.
Okay, but the time travel period suddenly becomes configurable. You can extend it way out, anywhere from 0 up to 90 days.
90 days? Wow.
Yeah, so that gives users almost 3 months of that self-service oops protection, the ability to go back and recover from user errors over a much longer time frame.
But just to be crystal clear, even if you choose, say, only 1 day of time travel on your Enterprise permanent table, or you choose the full 90 days,
Doesn't matter.
the fail-safe period remains that fixed, additional 7 days tacked on the end.
Correct. That 7-day platform recovery layer is always there for permanent tables, regardless of your time travel setting. And the fact that transient tables let you completely bypass that mandatory 7-day FS commitment, that's precisely why they are such essential cost-saving tools, especially for large enterprises dealing with massive data volumes.
That's a fantastic breakdown of the cost and resilience trade-offs. But speaking of, operational realities and how these things work day to day, let's pivot to something that I think often confuses new architects, maybe even seasoned developers sometimes. It's that peculiar behavior around naming conventions, specifically when temporary tables get involved.
Ah, yes. The naming conflict quirk.
Quirk feels like the right word.
It does feel like a quirk, but it's less of a design flaw, I think, and more of a really critical safety feature baked into Snowflake's architecture.
How so? Normally, in most database systems, if you try to create two objects with the exact same name in the same schema,
You get an error. Object already exists.
right. But Snowflake actually allows temporary tables to violate that uniqueness rule under certain conditions.
It does. Specifically, a temporary table can share a name with an existing permanent or transient table within the same schema.
Okay, let's walk through a scenario, maybe a slightly scary one. Imagine you have this huge, multi-terabyte, absolutely critical, permanent table. Let's call it production sales data.
Okay. Core business data.
Right. Now, in my own session, maybe I'm debugging a complex stored procedure, and I decide, just for my testing, I want to materialize some intermediate results into a temporary table. And I happen to name it production sales data as well. What happens? Does it fail? Does it overwrite the permanent one?
Neither. What happens is the temporary table takes immediate precedence within your session.
Okay.
It effectively creates this localized session-scoped overlay. It hides the existing permanent table from view, but only for you, only in your current session.
Whoa. So inside my session, if I run select from production sales data,
You'll get the data from your small temporary version.
and if I run, say, a delete statement on production sales data,
It only affects your temporary table. The underlying multi-terabyte permanent table is completely untouched and, in fact, totally inaccessible to you within that session while the temporary one exists.
that's actually brilliant. It's a safety mechanism.
Exactly.
It means you can run intensive tests, maybe simulate a big update or delete on what looks like a critical production table, but you're safely sandboxed, working only against your temporary disposable copy.
Precisely. It acts as an isolation layer. And scenario 2 is similar. Let's say your temporary production sales data table is active in your session, and then someone else, or maybe even you in a different session, creates a new permanent or transient table, also named production sales data.
What happens in my original session where the temporary one exists?
That new non-temporary table would also be hidden by your active temporary table. It wouldn't suddenly appear or cause a conflict in your session.
So the golden rule is basically the temporary object always wins any naming conflict, but only within its own session's scope.
That's the perfect way to put it. Within that session, all queries, all DML, anything referencing that name hits the temporary table. The underlying permanent or transient one is effectively invisible until that temporary table is either explicitly dropped or the session ends.
It seems like a vital mechanism to prevent potentially catastrophic accidental modifications during development, debugging, or testing phases.
Absolutely critical for safety. How to identify a Snowflake table type.
Okay, so given these really significant differences in persistence, cost, recovery, and even naming behavior, knowing exactly what kind of table you're actually dealing with seems paramount.
Oh, absolutely essential.
Yeah.
You need to know if you're looking at something permanent, something transient, or just a temporary workspace.
Fortunately, the sources highlight that Snowflake gives us several pretty clear ways to figure this out. Method 1 is probably the classic SQL workhorse, the show tables command.
Yep, show tables is usually your first stop. When you run it, say show tables in my DB, my schema, it lists all the tables that are accessible to you in that schema. And interestingly, it even includes tables that have been dropped recently, but are still recoverable because they're within their time travel window. Standard filtering applies.
Yeah.
But the crucial piece of information you're looking for in the output.
Is that column called kind?
Yes. The kind column is the definitive flag in the show table's output. It will explicitly tell you the type. It'll return table if it's a standard permanent table.
Okay.
Transient if it's a transient table, or temporary if it's one of those session scoped ones.
So no ambiguity there. Show tables tells you the kind.
Unambiguous declaration of the object's underlying architecture, and therefore its recovery rules and persistence.
Okay. Method 2 seems arguably even more definitive, especially for understanding the table's original creation intent. That's using the DDDD.
Key DDDL. Yeah, that function is incredibly powerful for any kind of object introspection in Snowflake, not just tables.
What does it do?
It literally returns the exact data definition language, the DDL statement, that was used to create the object in the first place.
The create table statement itself.
The whole thing. So if you run, say, select getly table, mydb.mytable, the result you get back will be the literal text of the command. It'll start with create table, if it's permanent, or create transient table, if it's transient.
Or create temporary table, if it's temporary.
Exactly. You see the key word for word, that was used when the table was born. So it's probably the most robust, most unambiguous way to confirm the type because it shows you the table's genesis. It directly ties back to that initial decision about cost and recovery.
Okay, and finally, method 3 involves querying the information schema. You know, the system-defined views, the data dictionary. This is often essential for any kind of large-scale metadata management or automation.
Right. You can query the table's view within the database's information schema.
Yeah.
Something like select from mydb.informationschema.tables, where table name mytable.
And that gives you lots of metadata, right? Table owner, creation time, row count estimates, size in bytes, all that good stuff.
All that good stuff. Excellent for getting a profile of tables across an entire database or schema, maybe checking for large tables, finding owners, etc.
But, and this seems like a really important but, this method comes with a critical, often forgotten caveat when it comes to table types.
It does, a very important one to remember. The information schema views, including information schema.tables, do not show temporary tables.
They just don't list them at all.
Not at all. The thinking is temporary tables are inherently transient. They're scoped only to a specific session, so they aren't tracked as part of the persistent shared database dictionary that the information schema represents.
Okay. So if I run that information schema.tables query looking for a table named mayTempWork, and that table is actually a temporary table active in my session,
you'll get an empty result set back from the information schema query. It will look like the table doesn't exist, even though you can query it directly in your session.
Yeah.
That sounds like something that could cause hours of confusion and debugging.
Oh, it absolutely does. You think a table exists, you can query it, but the system metadata views say it's not there. So the practical takeaway is, if you suspect you might be dealing with a temporary table, you must rely on the session-aware tools like show tables or getDDL to identify it. Don't trust the information schema for temporary table visibility. Knowing that little detail saves a lot of headaches.
Okay, we've covered the core trio, permanent, transient, temporary in detail, but we should probably briefly touch on an architectural outlier, something that operates completely outside these three categories of tables stored inside Snowflake.
You mean external tables?
Exactly, external table.
Yeah, they're absolutely fundamental to a lot of modern cloud data warehousing patterns. But you're right, they are categorized separately. And the reason is They fundamentally decouple the storage of the data from Snowflake's compute and management.
They aren't created directly inside Snowflake in the same way the other three types are.
Correct. An external table doesn't actually store the data bytes within your Snowflake storage layer. Therefore, it doesn't consume storage space that contributes to your Snowflake storage costs in the same way.
Okay, so if the data isn't in Snowflake, how do they work? What do they let you do?
What an external table does is allow users to access and query data from files that are stored in an external location, usually an object storage stage.
Like files sitting in Amazon S3 or Azure Blob Storage or a Google Cloud Storage bucket.
Precisely. It lets you query those files as if the data was housed in a regular Snowflake table.
How? What does Snowflake store then?
The key is that only the metadata about those external data files get stored within Snowflake itself. Things like the file paths, maybe partition definitions if you set them up, the structure schema of the data within the files, maybe some file-level statistics.
Gotcha. So Snowflake knows where the data is and what it looks like, but the actual data remains in S3 or Azure or GCP.
Exactly. When you run a query against an external table, Snowflake uses its compute engine to read the files directly from that external stage, process the data on the fly, and return the results. It's not responsible for managing the long-term storage of that data or its backups or applying time travel or fail-safe features to it. Those responsibilities remain with the external storage system, like S3, lifecycle policies, versioning, etc.
That sounds like it offers immense flexibility in certain situations.
It really does. Think about organizations with really strict data residency requirements. Maybe data must legally remain within a specific geographic region in, say, Azure Blob Storage.
Right.
Or think about companies that already have massive pre-existing data lakes built up over years in S3. External tables let them leverage Snowflake's powerful SQL engine and performance for querying that data lake.
Without having to physically migrate all that data into Snowflake first, and without committing to Snowflake's managed storage costs and specific persistence policies like TTFS for that entire data lake.
Spot on. That ability to decouple the storage location from the compute engine is a core benefit of the modern cloud data warehouse model. It gives architects and organizations vital options beyond just fully managed internal storage, especially when specific architectural constraints or massive existing data volumes demand it.
Okay, let's bring this deep dive home. Let's circle back to that core decision point. We've really established, I think, that choosing the right Snowflake table type, permanent, transient, or temporary, it's fundamentally an exercise in risk management, paired very closely with aggressive cost optimization. They go hand in hand.
Absolutely. The core lesson, I hope, is that building successful, efficient cloud data architectures relies heavily on consciously aligning the volatility of your data or its replaceability with the level of recovery capability you actually need.
You constantly have to ask those questions. Do we genuinely need user-driven time travel for this data set to recover from routine errors? And maybe more importantly, from a cost perspective, do we really need to pay the premium for platform-level fail-safe for this specific data just in case of catastrophic system failure?
And understanding that transient and temporary tables are the most powerful levers you have for directly controlling that cloud expenditure, especially when that full belt and braces disaster recovery from failsafe just isn't necessary.
Yeah, if you truly know that you can recreate the data from a source system or maybe from an external archive, then using a transient table instead of a permanent one saves you that often substantial premium you pay for the 7-day failsafe window.
Over the life of a big project with large data volumes, that saving could potentially run into the millions just on storage costs alone.
It's one of the most immediate, tangible impacts you can have on a project's budget and also on its resilience profile, just making that conscious table type choice up front.
Which leads us perfectly into our final provocative thought, something for you, the listener, to maybe chew on after this.
Okay, let's frame a scenario. Imagine a large global company. They're ingesting billions, maybe trillions of rows of IoT sensor telemetry data every single day. Huge volume.
Classic big data problem.
Now, maybe regulatory rules dictate they have to hold on to the raw ingested data for, say, 3 years. But for their day-to-day business analytics, their operational dashboards, they really only need to actively query the most recent 14 days of data.
Okay. Long retention required, but short active query window.
And their plan is anything older than maybe 30 days, they're going to archive off to a really cheap cold storage tier, maybe Glacier Deep Archive in S3, where storage costs pennies per terabyte per month.
Very common pattern. Hot, warm, cold data tiers.
Right. So the challenge, the architectural decision they face is, for that initial ingestion, that first 30 days of data before it gets archived, should they land it in a permanent table? Maybe with minimal time travel, say, one day.
Which
Which means they'd be paying the fail-safe storage premium on those billions or trillions of rows every day, data they fully intend to archive off within a month anyway.
or the alternative.
Or should they deploy that initial ingestion table as a transient table, explicitly zeroing out that potentially very costly fail-safe requirement?
And in that case, they'd be relying entirely on time travel for immediate operational recovery, and then on that cheap external S3 archive for meeting the longer-term, multi-year retention requirement if a major disaster recovery were ever needed for older data.
That trade-off. Paying the hidden, ongoing cost of the 7-day fail-safe on massive, highly volatile, yet ultimately replaceable data sets, versus consciously eliminating those costs entirely by choosing transient.
That is the immediate, real-world budgetary and risk assessment challenge facing pretty much every Snowflake architect working at scale today. And that decision balancing cost against platform-level resilience is the defining architectural question that hopefully you now have the tools and the context to answer much more confidently.
We certainly hope this deep dive helps you navigate that decision strategically for your own data.
Thanks for diving deep with us today.
We'll catch you on the next one.